This lecture going to explore principles underlying carbon dioxide removal from the atmosphere. I'm L3.3, a professor from Cornell University. In this lecture, I'll cover 4 topics. The first one is the relationships between global warming and greenhouse gas emission. The second one is the need of carbon dioxide removal. The third one is land-based CDR strategies. And the last one is the principles of evaluating and design carbon dioxide removal strategies. I'll talk about the relationships between global warming and greenhouse gas emissions first. As you may know, global surface temperature has increased by about 1.1 degree above that in a pre-industrial. The model has predicted that global surface temperature may increase up to 4 to 5 degrees by 2100 under the high emission scenario. It is also possible that global surface temperature may increase only by 2 degrees or even 1.5 degrees by end of 2100 if the carbon emissions are strictly limited. And also, as the temperature increases, it causes many of those so-called catastrophic consequences, such as wildfires, extreme drought, and hurricanes. And in the past research, it has been conceptually illustrated as shown at the left panel that as the greenhouse gas accumulated in the atmospheres and it extract the long wave radiative heating and less heat lost from the atmosphere and the more it trapped in the atmosphere and caused warming. Recent study has shown that global surface temperature increases linearly correlate the cumulative amount of greenhouse gases emissions in the atmosphere. So the linear relationship showed that for every 1,000 gigaton carbon dioxide equivalent greenhouse gas accumulated in atmosphere, the global surface temperature increased by about 0.45 degrees Celsius. So in order to limit the global warming, we need to have the carbon dioxide removal, which I'm going to explain in the next few slides. To limit climate warming to 2 degrees or even 1.5 degrees with no or limited overshoot, we need to reduce greenhouse gas emission together with carbon dioxide removal. In this figure, you may see the term nationally determined contributions, NDCI. Let's talk about this term first. Nationally determined contributions, abbreviated to NDCs, are national plans that the government aim to implement in response to climate to achieve the global targets of reduced greenhouse gas emissions and limit the anthropogenic climate warming to well below 2 degrees Celsius, preferably 1.5 degrees Celsius, relative to the pre-industrial level by 2100. NDCs include actions to reach net zero emissions, increase adaptations to harmful effects of climate change, and adjust the financial flows for supporting greenhouse gas emissions reductions. Reduce emissions and carbon dioxide removal are the two primary tools to achieve net zero emissions. Specifically, emissions reduction can occur through improved resources use efficiency, sustainable development, and substituting the fossil fuel energies with renewable alternatives. This slide shows the two components to achieve net zero. The conventional mitigation technologies, including uses of solar energies and green technology, will reduce greenhouse gas emissions. But there are sectors of economy where greenhouse gas emissions cannot be cut to zero. Then we need to develop carbon dioxide removal technologies to compensate such emissions. Carbon dioxide removal results in negative greenhouse gas emissions. Carbon dioxide removal, defined as a process in which carbon dioxide is removed from atmosphere by deliberate human activities and durably stores in geological, terrestrial, or ocean reservoirs or in products. We need to remove about 3 gigaton carbon dioxide per year to limit the climate warming to within 1.5 degrees Celsius by 2100 under a low energy demand scenarios with numerous optimistic assumptions on technology advances and lifestyle change. But we need to remove 20 gigaton carbon dioxide per year under a scenario for fossil fuel intensive economic development with a high energy demand. There are two types of carbon dioxide removal, the natural-based and the technology-based method. The nature-based climate solutions emphasize the sustainable management and the use of natural features and processes for reducing greenhouse gas emission and the store carbon in land and ocean ecosystems. The technology-based method include direct air capture with carbon sequestration, biochar carbon removal, enhanced rock weathering, and bioenergy with carbon capture and stores, so-called BCAS. Now let's talk about land-based carbon dioxide removal strategies. The land-based carbon dioxide removal strategies include afforestation, reforestation, agricultural practices that sequester carbon in soils, such as carbon farming, wetland, and coastal restorations. There are dozens of land-based methods to remove carbon dioxide from the atmosphere. Afforestation and reforestation may remove about 9 gigaton carbon dioxide equivalent per year from the atmosphere using available technology, but only more than 1 gigaton carbon dioxide equivalent per year based on the cost-effective approaches. Similarly, agroforestry may be technically able to remove nearly 6 gigaton carbon dioxide equivalent per year from the atmosphere, but only about 1 gigaton carbon dioxide equivalent per year based on cost-effective approaches. That we need to understand the two types of potentials of land-based CDR. The Technically potential are the possible removal of carbon dioxide with available technology, regardless of the cost. On the other hand, cost-effective mitigation potentials are the more realistic and achievable target grounded in public willingness to pay for climate mitigation and therefore are more relevant in policymaking than technical potentials. The cost-effective potential may deliver 8 to nearly 14 gigaton carbon dioxide equivalent per year between 2020 and 2050. There are sector differences in mitigation potentials. Restoration in forest and other ecosystems and improved agriculture may remove more than 20 gigaton carbon dioxide per year for technical and 6.6 gigaton carbon dioxide per year for cost-effective. That exclude bioenergy and carbon capture and storage. Agricultural, agroforest, biochar, and soil carbon sequestrations may remove 4.8 gigaton carbon dioxide per year, with a cost up to $100 per ton carbon dioxide. Bioenergy and carbon capture and storage may remove 2.5 gigaton carbon dioxide equivalent per year and 0.5 gigaton carbon dioxide equivalent per year respectively, with technical and cost-effective potentials. Here we need to talk about agriculture, forestry, and other land uses, so-called L3.3 mitigation. L3 reduce greenhouse gas emissions and enhanced carbon dioxide removal through supply-side interventions in forests and other ecosystems, i.e. protection, management, and restoration. Agriculture, i.e. reducing emission and enhanced carbon sequestrations. Bioenergy, i.e. reducing fossil fuel emissions and sequestering carbon. Almost all countries have included L3 measures in their NDCs under the Paris Agreement, either as a specific list of actions or by including the land sector in broader greenhouse gas reduction target. L3 make up about 25% of planned greenhouse gas reductions globally, with most focus on the reducing deforestation. Now let's explore principles for evaluating and design CDR strategies. Removing carbon dioxide from atmosphere to store in the land ecosystems require creation of land carbon storage pools. Then we need to understand what determines carbon storage in terrestrial ecosystems. Land carbon storage is determined by two parameters: carbon input and residence time. Carbon input determines the amount of carbon getting to the storage pool. The residence time determines how long the carbon can stay in the pool. As shown in these slides, carbon storage in land ecosystems is the product of carbon input and the residence time. The uppermost contour represents the carbon storage of 3,000 gigaton. The lowest value is 1,000 gigaton. There are output of three models. The Canadian model generates the highest carbon storage because of its highest resonance time. In comparison, CSM-BGC has the lowest carbon storage because of its low carbon input and resonance time. Now let's examine how those two parameters change with afforestation. When we convert a cropland to forest, carbon input via gross primary production may increase slightly or may be even similar. But there are fractions of a carbon input that's used to grow woody biomass, so that resonance time for carbon in the ecosystem increased. We used a similar way to examine each of the land-based carbon dioxide removal methods. Afforestation and reforestation may increase carbon input slightly but substantially lengthen carbon resonance time. Similarly, coastal wetland restoration may increase carbon input slightly but substantially lengthen carbon resonance time. Peatland restoration greatly lengthen the resonance time with a little change in carbon input. Most of the land-based carbon dioxide removal substantially increased carbon resonance time with a little change in carbon input. So there is a very large range of change to be implemented for resonance time, but a relatively small range of change in carbon input. Indeed, there are many ways to lengthen resonance time. For example, afforestation and reforestation may lengthen resonance time by 50 to 300 years. Biochar may extend the resonance time by more than 100 years. Creating wood products such as furniture may lengthen resonance time for 20 to 100 years. Preserving wood debris in deep soil may lengthen resonance time up to 5,000 years. Little under anaerobic conditions, such as peat in peatland, may extend the resonance time for 300 to 5,000 years. Professor Ning Zheng at the University of Maryland has studied the preservation of wood debris in soil vault for a long time. His study has indicated that preserving wood debris in deep soil may lengthen resonance time for thousands of years. It becomes a very effective land-based carbon removal strategy. Carbon dioxide principles we propose to evaluate land-based carbon dioxide removal strategies are consistent with existing criteria. Traditionally, CDR methods need to be evaluated with at least 3 criteria: additionality, permanency, and avoiding leakage. Additionality is the increased amount of carbon that is being stored because of implementation of CDR technology. Permanency or durability is the duration for which carbon dioxide can be stored in a stable and safe manner. Avoiding leakage is that CDR activities should not cause emission at other geological locations due to market or other shift. Those criteria are quite qualitative. Use the carbon cycle principles as we discussed. We can define those terms as much more quantitative. For example, additionality can be measured by increasing carbon influxes or lengthening resonance time or both. permanency is measured by carbon dioxide or carbon residence time. And avoiding leakage is demonstrated by quantifying carbon influx or residence time and showing there is no decrease relative to reference conditions in the regions of study. In summary, carbon dioxide removal from atmosphere results from either increasing carbon input, lengthening residence time, or both in the carbon storage pool in the land ecosystems. It is critical to quantify changes in both carbon input and residence time when we evaluate the effectiveness of CDR towards carbon neutrality. We may also design new CDR strategies by finding ways to either increase carbon input, lengthen residence time, or both. Thank you very much for studying this lecture.